Hello, welcome back to my channel. You may be aware that over the last few months I've been putting together resources for revision for a variety of different exam boards. Today is a video that is mainly focused for GCSE, although if you are studying A-level could also be helpful as a baseline for what you need to know going into A-level geography, for those of you that might be picking up geography now, ahead of next year, doing A-levels and things like that. This is the baseline that you would be expected to know. This is AQA GCSE geography specific. However, when it comes to physical geography, it's so applicable to each of the exam boards. So if you study EDUCAS, if you study OCR, if you study EdXL GCSE, you will cover natural hazards in one way or another. Tectonic hazards, tropical storms, tsunamis, earthquakes, volcanic eruptions in one way or another. And so, yes, whilst this falls under the title of the AQA Geography GCSE spec, it's not specific to that. So we're going to cover this today as a bit of advanced warning. Warning's not the right word. Basically, if you study this spec, down below in the comments is a link to a revision homepage. If you are one of my students, you will have already seen this for your spec, but this is for the GCSE AQA Geography. On there has loads of multiple choice questions that you could go and answer. There's Quizlet courses there. There is links to all of the online revision guides, just so it's all in one place. Feel free to share that. It is completely free. And I just thought it would be useful for people to have. There is also an email address on there that if it comes close to your exams and you're stressing about one thing or another, where it's one form of content or how to answer this particular question, there is also an email that you can drop an email to with a template of an email, essentially of how to book a tutoring session with me, if that is something that you think will be helpful in the lead up to your exams. Obviously, I teach full-time, so it would be in my evenings and weekends and things like that, and availability is somewhat limited because I already do tutor alongside my work anyway, so please do bear that in mind. If that is something you think will be useful, that is a good place to start soon-ish. If you don't do GCSE geography or don't do AQA for GCSE geography, drop me an email on the email below and I can get you set up with the link for your specification as well. It's on an app or website called Notion. It is completely free of charge to use, to access, although some of the links to download content and things like that are more specific to certain topics, and you can really only download them on a computer. So just a bit of advanced warning. It looks a little bit like this. This is the homepage for AQA Geography. Hopefully you'll be able to see that on the screen. And you'll be able to see the revision videos. I'll link all of these on there so that you don't have to scroll back through my YouTube channel. You can just see it all on there where you need them. There's a bunch of past questions and there's recall questions, that kind of thing. So it's all on there for you. Please do make the most of it. Hopefully I will put a community post up later this week as well, explaining that too. But yeah, it's all there for you if you need it. So there's my little spiel as a bit of a starter, but let's get going. So we're going to think about the challenge of natural hazards. So what actually is a natural hazard? This is a hazard that has the event to cause potential harm to the environment, people, or an economy. A natural hazard is an event caused by the environmental processes that will occur within the world without the presence of humans. The term hazard is used because of the potential impact when a natural event occurs and its impact on humans. A disaster occurs when harm actually occurs to the environment, people, or economy. So, some examples of our tectonic hazards. We have earthquakes, volcanic eruptions, landslides, tsunamis. Our geomorphological hazards are our floods and landslides. Atmospheric hazards are tropical storms, droughts, tornadoes, cyclones, whatever else you want to call them, hurricanes. They all come under that umbrella of tropical storms. And then our biological hazards are things like pests and diseases. So, what affects hazard risk? A hazard risk is the chance that an area or population will be affected by a natural hazard. There are a variety of factors which affects the level of hazard risk within a particular area. The first of which is population. As world population increases, more people live in areas which are vulnerable to natural hazards. Urbanisation and population density also have a role to play. So as urban areas are generally more densely populated, there are increasing numbers of people who are at risk within urban areas. Frequency and magnitude of some hazards isn't increasing. So our tectonic hazards aren't increasing because they are natural processes. They are not increasing as a result of climate change, but things like our geomorphological hazards, so floods, landslides, and our atmospheric hazards, so tropical storms, droughts, tornadoes, are increasing as a result of climate change. Because the energy of the heat in the atmosphere needs to go somewhere, and it goes into our weather. Levels of development also affect the hazard risk of a country. So generally, the more high income a country is, the more well prepared they are for a hazard event. Whereas our lower income countries and our newly emerging economies struggle more when a hazard event occurs. Prediction methods also help to influence the effect that a hazard has on an area. So the more prepared we are and the more we predict a hazard, generally we can't predict them all, but we can predict some of them, the better people will be. And human activities such as deforestation and urbanisation also increase hazard risk. So let's think about tectonic hazards. Plate tectonic theory says that you need to know about the Earth's structure. So there are 4 layers to the Earth that you need to be aware of, going from the inside outwards. Firstly, we have the inner core. This is about 1,400 kilometres in diameter, so across. It's solid and a dense layer composed of iron and nickel with temperatures of about 5,500 degrees centigrade. The outer core, moving out, is 2,100 kilometres thick, and it is a semi-molten metal layer with temperatures between 5,000 and 5,500 degrees centigrade. The mantle is about 2,900 kilometres thick and is a semi-molten layer which is less dense than the outer core, and then the crust, its thickness varies depending on where you are. It can go from 20 kilometres thick up to 100 kilometres thick, and it is made up of the 2 different types of crust. One being oceanic, which is thinner but heavier and more dense, and then our continental crust, which is thicker, all the way up to 90 kilometres thick, but it's older and lighter in density. The oceanic crust is continually being created and destroyed as a result of plate movement, where it is denser and so subducts under the continental crust, even though it's thinner. This is why continental crust is much older than oceanic crust, as it isn't destroyed. The crust is broken into a number of tectonic plates. These plates move on top of the semi-molten magma below, in the mantle, and plate tectonic theory once stated that the movement of these plates was as a result of convection currents in the mantle. So this movement, as it's hotter in the centre, that heat rises and pulls the semi-molten magma towards the surface, cools as it's at the crust, and then falls back down towards the outer core again. And it's convection currents that are pulling the crust. This is where we have subduction going on and slab pull. The Earth is made up of different plates that all fit together a bit like a jigsaw. You know, there are 2 types of plates, oceanic and continental. The continents of the Earth have not always been in the place that we know them today. Alfred Wegener had a theory that continents used to be a supercontinent called Pangaea that existed 250 million years ago. He called his theory continental drift, and it existed in 1915. That's when the theory came out. However, people didn't really believe him until he then died, and then in the 1960s, plate tectonic theory was more widely adopted as the way that the plates have moved. In 1929, a man called Arthur Holmes proposed the idea that it was convection currents under the mantle that were moving the plates. So, what about this distribution of earthquakes and volcanoes around the world? So, earthquakes occur at all plate boundaries, but about 90% of the earthquakes on our planet occur around the Pacific Ring of Fire. Most volcanoes occur at constructive and deconstructive plate boundaries, so they do not occur at conservative boundaries. The majority of active volcanoes, about 75% of them, are located on the edge of the Pacific Ring of Fire. However, there are things called volcanic hotspots, which occur away from the edges of plate boundaries and are plumes of magma which break through the Earth's crust because it's thinner. So a really good example of that would be either Hawaii or the Canary Islands. They are volcanic hotspots. So let's think about the physical processes at plate margins. Plates can move away from each other, they can move towards each other, or they can slide past one another, depending on the speed and direction of the types of plates. So at a constructive margin, this is when the plates are moving apart. New land is formed in the middle or constructed, which is why it's a constructive margin. Iceland and the Mid-Atlantic Ridge is an example of this, where the plates are moving apart. We sometimes also call these divergent margins. The large-scale landforms we find here are shield volcanoes. Earthquakes can also form here, but they're not very strong generally because there's no build-up of pressure. And then our small-scale landforms that we find here are things like geysers or geysers, however you'd like to say it, and lava tubes. So a geyser is a rare kind of hot spring that is like under pressure and then erupts. You've probably seen a picture or a video of it, or you might have seen one yourself if you've ever been to Iceland, and it sends jets of water streams into the air. Geysers are made from a tube-like hole in the Earth's surface that runs deep into the crust. That water is then boiled because of the heat and sent up towards the surface. Lava tubes are a natural tunnel with solidified lava that was formerly occupied by molten lava but is now formed in the shape and basically formed rock. Okay, next we have our destructive plate margins. This is where land is being destructed, plates are moving together, land is being broken down, or oceanic plate is being broken down. This is where we find a lot of stronger volcanoes, so our composite volcanoes, or our cone volcanoes, or our stratovolcanoes, whatever you'd like to call them. We also have a lot stronger earthquakes here. We have a deep oceanic crust. That's what happens at our destructive margins. We sometimes also call these convergent margins because they're moving together, but destructive is perfectly acceptable. So, as our oceanic crust meets our continental crust, one subducts beneath the other. We also have something called a collision margin. So this is where two continental crusts are still moving together, but as I've already told you, no continental crust is ever destroyed. So instead of one subducting beneath the other, because they're of the same density, they both get pushed upwards. And this is a collision plate margin, and they form something called fold mountains. No magma is present here, but they do form high mountains, such as the Himalayas and Mount Everest. And then our final kind of plate margin that you need to be aware of is a conservative plate margin. This is where the plates slide past each other, either in opposite directions or in the same direction, just at different speeds. So no land is created or destroyed, no volcanoes are present here. However, we do have very strong earthquakes because of a build-up of pressure that is then released. We call this a transform boundary, and a really good example of this is in California on the San Andreas Fault, where the North American plate meets the Pacific plate and causes strong earthquakes. So what about some of these effects of earthquakes? They have both primary and secondary effects. The primary effects are caused directly by the earthquake, such as damage to buildings, cracks in roads, and they are usually limited to the areas closest to where the earthquake happens. But our secondary effects can go much wider. So these are caused indirectly by the earthquake. So, such as fires caused by broken glass, or avalanches, or landslides. These usually last longer than the original earthquake, and they happen as a result of the earthquake rather than the effects of the earthquake itself. So how do we respond to earthquakes? We measure earthquakes generally now by the Mercalli scale. This is a measure that was thought up by the Italian volcanologist Giuseppe Mercalli in 1906, and it measures earthquake intensity, how strongly the earth shakes and what damage it does. And it's rated on a scale of 1 to 12. However, it's often inaccurate and we don't use it very often now because it depends on personal judgment and it depends where you are and if you're describing that accurately. Whereas we do now use the Richter scale. This is a measure of earthquake's magnitude, how much energy is released in an earthquake. It doesn't rely on people's opinions, but on measurements of energy. And it's measured on a scale of 1 to 10. However, the biggest earthquake we have seen on Earth is a 9. We don't know if the Earth can actually create an earthquake that is above a 9. We don't know if it has that tectonic power. We need a seismograph to measure how much of an impact an earthquake has and its magnitude. So if an earthquake is detected, the seismograph allows for how far away the earthquake can be felt and how deep the earthquake was and how powerful it is. So we're going to compare two different earthquakes and look at some of these effects. One you've probably come across, even if you're not doing it as your case study, was the Japanese earthquake in 2011. It was a 9.0 on the Richter scale, and it occurred 129 kilometres off the east coast of Japan. It was 32 kilometres deep, so a fairly shallow earthquake at a destructive margin, but Japan is a high-income country. So 1,600 people died. The earthquake lasted 5 minutes, and it did cause a tsunami that had a big natural disaster associated with it. We call it the Fukushima disaster, in which the tsunami flooded a nuclear power site and therefore resulted in lots of nuclear waste being exposed, and a lot of people died as a result of that. In comparison, Nepal is a low-income country, and there was an earthquake in 2015 on the Richter scale of 7.9. It was a very shallow earthquake at 8 kilometres deep, and it occurred 60 kilometres away from the capital in Kathmandu. It's on a collision plate margin, so not a destructive one, but a collision, so two continental plates coming together. Nepal is where we find the Himalayan mountains. The quake lasted for 6 minutes, 8,000 people died, and 19,000 people were injured, and there was massive structural damage within the capital city of Kathmandu. But any responses to an earthquake can be divided into two groups: immediate, which is the days that follow the earthquake, and longer term in the months afterwards. So our immediate responses: rescue teams went in search for survivors, medical assistance could be provided for those people injured, shelter for the homeless, food and water provided, and a lot of these come from international organisations, or what we call NGOs, non-governmental organisations that come in and help with the recovery effort. But there are also more long-term responses, so things like building homes, rebuilding buildings, improving building regulations, improving evacuation plans, education, repairing water supplies, money from international governments to help rebuild the economy, building transport routes again. These are all different ways that long-term responses can help a country to recover. So, how do we reduce the risk from tectonic hazards? There are 3 P's that you need to be aware of. Firstly, prediction. There may be many pre-shocks to an earthquake, which can be measured on a seismograph, but there might also be a period of relative stability where there's this build-up of pressure. We saw this in Japan, and so there was this build-up of pressure, and then there was this massive earthquake and lots of aftershocks afterwards. Animals will also act strangely, such as dogs will howl before an earthquake. They can generally predict what's going to happen. It's really hard to use animals because it's, again, biased. We can't always predict it using animals, but they can be a good indicator. We can then also think about preparation. So we can prepare disaster plans, organise and prepare hospitals and evacuation centres. We could organise emergency supplies and how to get into particular areas. And then we can also protect. So Japan does this really well. They have introduced protection measures and they have introduced earthquake-proof buildings to be able to withstand the effects that earthquakes have. They know they are in a very tectonically active zone and therefore are at risk of a lot of earthquakes. And so being able to prepare for that because they have the money to do so was a reason that there weren't as many deaths in Japan following a stronger earthquake than that in Nepal. We can have robust shock absorbers on the foundations of buildings to absorb the tremors. Steel frames can sway in the earth's movement rather than concrete, which can shatter. There can be lots of open outdoor areas where people can go safely in an evacuation. These are all ways of protecting against tectonic hazards. Okay, let's think about some weather hazards. So, when it comes to weather hazards, you need to be aware of global atmospheric circulation. Now, this is one of the aspects of geography that students find really hard because it feels very abstract. So, we're going to break it down step by step. The movement of the air across the Earth occurs in a specific pattern, and the whole system is driven by the equator, which is the hottest part of the Earth. So, air rises at the equator, leading to low pressure and rainfall. When the air from the equator reaches the edge of the atmosphere, it can't go any further, and so it travels to the north and to the south. It happens the same way in the northern hemisphere as it does in the south. As this air starts to become cold and fall, it creates high pressure and dry conditions at around 30 degrees north and south of the equator. Large cells of air are created in this way, and we call this the Hadley cell. Air again starts to rise about 60 degrees north and south and descends at around 90 degrees north and south. So we have the polar cell going on at the poles, we have the Hadley cell going on at the equator, and the one in the middle, which dictates the UK's weather, is what we call the Ferrel cell. Global atmospheric circulation creates winds across the planet and leads to areas of high rainfall like the tropical rainforest and areas of dry air like the Sahara Desert. If you pick up the revision guide, there is something that will be very helpful for you in there, especially when it comes to the global atmospheric circulation model. It's got it all described for you there, and it will be a lot easier. So let's think about tropical storms. A tropical storm is a very powerful low pressure weather system which occurs as a result of strong winds and heavy rainfall. Tropical storms have different names depending on where they occur in the world. In the US and the Caribbean, we know them as hurricanes. In South Asia, they're known as cyclones. In East Asia, typhoons. And in Australia, they're known as willy willies. And they all develop in the same way and have the same characteristics. So they all come under this umbrella term of tropical storms. So tropical storms are rotating, intense, low pressure systems, and they develop over warm tropical oceans above 26.5 degrees, between 5 and 30 degrees north and south of the equator. They never ever cross the equator. When winds converge or meet near the ocean surface, and where there is low vertical wind shear. So, the relationship between global atmospheric circulation and tropical storms. They are mostly related to the Hadley cell, the Coriolis effect, and the equatorial trade winds. So, if you've looked over the global atmospheric circulation at all, it's all there for you. I will also leave a video down below that I've done specifically on the global atmospheric circulation. And if you get access to that revision homepage, there's some from the Met Office as well that I will leave linked for you. So, the warm equatorial regions receive intense solar heating from the sun, raising the ocean temperatures. This warm, moist air rises, leading to an intense low pressure zone between the two Hadley cells, which is what we know as the Intertropical Convergence Zone, or the ITCZ. This generates thunderstorms, strong winds, intense rainfall, all at the surface. These are typical weather conditions at the rising arm of the Hadley cell. Dry air starts to descend, creating a high pressure zone at the surface. And this generates a high pressure gradient between intense low pressure and intense high pressure, generating the winds that form the tropical storm, moving from one to the other. If you think about it in terms of concentration, you've probably studied it in either chemistry or physics, and how if you've got an area of low concentration and an area of high concentration, when you remove that barrier, the dispersion happens very quickly. Again, that's what's going on here. So the trade winds move in a westerly direction from the equator, where the Coriolis effect starts to spin the air from 5 degrees north and south of the equator. If the effect is too weak at the equator, these start to move further north and south, and the spin is anti-clockwise in the northern hemisphere but clockwise in the southern hemisphere, as they are low pressure systems. The greater the low pressure, the greater the winds, and the greater the spin, and the larger the tropical storm becomes. So let's think about the structure and features of tropical storms. In appearance, a tropical storm looks like a huge whirlpool, a gigantic mass of moist, revolving air. Tropical storms are between 482 to 644 kilometres wide and 6 to 8 kilometres high. They move forwards at speed of 16 to 24 miles an hour, or kilometres an hour I should say, and can move as fast as 65 kilometres an hour. The Coriolis force is caused by the rotation of the Earth, which causes the tropical storm to spin. The central part of the tropical storm is known as the eye. The eye is usually 32 to 48 kilometres across, and it's an area of lighter winds and no rain, but it has a lot of falling, descending air. They can find large towering cumulonimbus clouds around the eye, and these are caused by warm air condensing as it rises, which leads to heavy rainfall and wind speeds of up to 320 kilometres an hour. So tropical storms develop between 5 and 30 degrees north and south of the equator. Because the easterly winds, they generally move westwards. The air above the warm ocean is heated, and once the ocean reaches at least 27 degrees, the warm air rises quickly, causing an area of very low pressure. As the air continues to rise quickly, it draws in more warm, moist air, rising up from the ocean, leading to strong winds. The rapidly rising warm air spirals, cools, condenses, and forms large cumulonimbus clouds. And these clouds form the eye wall of the storm, producing heavy rainfall. In the centre of the storm, however, cold air sinks, forming the eye of the storm, where conditions are calm and dry. So the impact of climate change on tropical storms. Climate change could lead to more locations being affected by tropical storms. Warmer seas could see the source area where the areas start to form extend further north and south of the equator. It's unclear whether climate change will increase or decrease the number of hurricanes, but climate models predict their intensity might increase. The following factors will play a part. So there's warmer ocean temperatures and higher sea levels. Wind speeds possibly will increase, and rainfall rates in these storms are projected to increase by about 20%. Sea level rise is also likely to make tropical storms more damaging, leading to more coastal flooding and more subsequent damage along coasts. Low-lying coastal communities where the population density is high and the income levels are low are most at risk. And there are also more people living in coastal communities in the future, which means that more people will be affected. Now, you will each study a different tropical storm, but if you study Typhoon Haiyan, there is a whole... Actually, you know what I'll do? Click on that link below, find the geography homepage, go into the challenge of natural hazards, and I will try and find some resources on a variety of different tropical storms for you, because there's no point me going through just one if you don't all do it anyway. And then if you would like to pick up the revision guide, it's all in there for you too. So, reducing the effect of tropical storms. There are several specialist tropical storm forecasting centres, such as the World National Hurricane Centre in Miami in Florida. The centre uses satellite images, various weather instruments and computer-based prediction systems to monitor, detect and track tropical storms. When a tropical storm affects a populated coastal areas, they are predicted and the centre issues warnings. You might remember this with Hurricane Helene not too long ago. Warnings also give the information to local authorities which are likely to be placed in the storm's path in order to make preparations for the protection of public safety. They are broadcast over the TV and radio, and warnings can be issued to people quickly and within enough time. They can also use reinforced aircraft fitted with various scientific instruments to fly through and over the tropical storms to collect data on it, which can be used to help to track and predict the path of a tropical storm. Okay, let's think about weather hazards within the UK. So, an air mass is a large body of water, or large body of air, I should say, with a similar temperature and moisture content throughout. Air masses can be small, or they can be gigantic, covering for thousands of miles. Air masses over water are called maritime air masses, and they include a lot of evaporated moisture. The air masses that come from over land are called continental air masses, and they are much drier in the air. Depressions are areas of low pressure. They have warm and cold fronts, where the fronts are very warm and cold. The fronts are where warm and cold air meet. Along the fronts, you often get rainfall. Winds blow anti-clockwise from a westerly direction, all to do with the Coriolis effect. The wind forces can be gale force, and you can tell this when the isobars are close together. An occluded front is where the area of cold front catches up with the warmer front, pushing underneath it and forcing it upwards. Eventually, there will be no warm air left at the surface, and occlusions tend to wrap around the centre of a low pressure, with a narrow band of thick cloud which produces heavy rain. Depressions in the UK bring a lot of rainfall. You've probably heard of the word depression before in relation to mental health, feels low, so low pressure leading to rainfall. That's a helpful way to remember it. And then we have anticyclones, which are the opposite. These are an area of high pressure. They don't have fronts and they can bring stable weather conditions. In the summer, high pressure can bring hot and dry weather. However, in the winter, they can bring very cold weather, although not usually snow. The winds are often light and blow in a clockwise direction from the east. So our summer anticyclone weather conditions bring fine, calm days, long periods of sunshine, cloudless skies, heat waves. They may be colder during the nights due to no cloud cover. And after a few days, the air starts to feel a bit muggy, and we often then have a thunderstorm as a result. However, our winter anticyclone weather conditions bring dew and frost in the morning, fogs, cloudless skies, and cold nights due to no cloud cover. So, climate change. What is the evidence for climate change? The global climate has been changing lots of times, and has been doing so over the past 30, 40 years, and will continue to do so into the future. The Earth's temperature has fluctuated in the last 100 years. However, since around 1950, there has been a dramatic increase in global temperature, known as global warming. So what evidence do we have of this? We have thermometer readings, which have been tracked over time, and we can see that the Earth's air temperature has increased around 1 degree on average since 1900. However, some areas around the world will increase in temperature quicker than the others, such as the Arctic and Antarctica are increasing about 4 times quicker than the rest of the world, which leads to rapid ice melt in those regions. We can also have evidence of climate change through glacial retreat. So over the last 50 to 100 years, photographic evidence has shown that the world's glaciers have been melting, causing them to retreat. And this increase in global temperatures is causing glaciers to disappear and increasing the melting of sea ice in the Arctic. Ice cores. Scientists sometimes use ice cores to detect changes in temperature. When snow falls, it traps air in the ice. And when scientists take a sample of the ice, it reveals the atmospheric gas concentrations at the time that the snow fell. This is used to calculate the temperature at the time. The ice can reveal temperature of each year for the past 400,000 years. And scientists that study ice cores say that there is clear evidence that there has been a rapid increase in temperature in the last few decades. And then we can also use early spring. So in recent years, there have been signs of a seasonal shift. Spring arrives earlier and winters tend to be less severe. These seasonal changes affect the nesting and migration patterns of wildlife. And then rising sea levels. Between 1900 and 2019, the average global sea levels rose by 0.21 metres, so 21 centimetres over 100 years. So what are the natural and human causes of climate change? The natural function of the Earth's atmosphere is to keep in some of the heat that is lost from the Earth. This is known as the greenhouse effect. The atmosphere allows heat to come in from the sun through shortwave radiation to pass through the Earth's surface. The Earth's surface then gives off heat. It's reflected back, known as long-wave radiation. This heat is trapped by greenhouse gases such as methane, carbon dioxide and nitrous oxide, which radiates the heat back towards Earth. And this process heats up Earth naturally. So, factors of humans increasing this global warming and the enhanced greenhouse effect, such as burning fossil fuels, such as coal, oil and gas, which release carbon dioxide into the atmosphere, creating a thicker layer of greenhouse gases, trapping more of that long-wave radiation. Deforestation, as trees absorb carbon dioxide, if we're cutting them down, there's less absorption, but also when we burn those trees, that releases the carbon back into the atmosphere because they're a carbon store. So dumping waste in landfill means that when the waste decomposes, it produces methane, which again is a greenhouse gas. And agricultural practices lead to the release of nitrous oxide into the atmosphere, but also harvesting lots of cows produce a lot of methane as well. There are, however, natural factors increasing global warming which contribute to it. The Earth has gone through periods of glacial and interglacial periods. We've gone through about 4 cycles of that in the last 450,000 years due to something called Milankovitch cycles. So we can have orbital changes. So currently, if this is the sun, we're going around the sun in a pretty circular motion, which means that throughout the year, we are in this interglacial period. However, there have been times in the Earth's history that we move around in a more kind of rugby ball shape. So there are times that we are much, much further away from the sun, which leads to glacial periods. Milankovitch has 3 different theories. We've got the wobble, in which the axis of the Earth changes ever so slightly. So the more extreme the axis, the more extreme our seasons are. We've got our orbital changes, going from a more circular motion to our elliptical motion. And as we move into that ellipsis, we are further away from the sun and therefore enter a glacial period. Okay, then we've got volcanic activity. So during a volcanic eruption, carbon dioxide is released into the atmosphere, which can increase global warming. However, temporarily, if there is ash in the atmosphere, that can stop some of the shortwave radiation coming in and lead to global cooling temporarily. And then solar output. So there can be fluctuations in the amount of radiation from the sun. If there's a high amount emitted, there'll be an increase in Earth's temperature. So the impacts of climate change on the UK. Sea levels could rise, covering lowland areas, particularly in the south and the east of England. There could be increased droughts and floods as more extreme weather increases. There could be an increased demand for water in hot summers, putting pressure on water supplies. And industries could be impacted, such as Scottish ski resorts may having to close due to a lack of snow. But around the world, sea level rise is predicted to affect about 80 million people. Tropical storms will increase in magnitude, species will be affected and may become extinct, migration patterns change, diseases such as malaria will increase as the band of where those mosquitoes can currently live is like this. As that band gets wider, because the temperature increases in a variety of places, there'll be more people susceptible to getting malaria from mosquitoes because they can now live in a wider range. And an additional 280 million people are likely to be affected. So, finally, managing the impacts of climate change. We have mitigation strategies, which is aiming to prevent the effect of something similar happening. So we can use alternative energy, such as solar, wave, tidal energy, to reduce our use of fossil fuels and will reduce the amount of CO2 going into the atmosphere. We can catch carbon. So there's already a lot of carbon dioxide within the atmosphere. There is a strategy called carbon capture and storage. So we're essentially taking that carbon out of the atmosphere and pumping it back underground, which will reduce the amount of carbon in our atmosphere, leading to hopefully reduction in overall global temperatures. We can plant trees because you know that they absorb carbon dioxide from the atmosphere. And then international agreements as well. So we've had the Kyoto Principle, we've had COP conferences, we've had the Sustainable Development Goals, we've had the Paris Agreement in 2015. These are all international agreements that have asked governments to pledge to reduce their carbon emissions. We'll see if that happens. And then adaptation strategies. So agriculture. Farmers will have to adapt some crops that they may not be able to grow in warmer or cooler climates. And other crops will be planted. Adaptation, we essentially want to respond to the climate crisis and what we can do with that. Water supply will change, so we can use water transfer schemes. This is where water is transferred from one area to another. And reducing the risk of sea level rise may include sea defences used to protect the land and stop it being eroded away. So I do hope this has been useful. Do subscribe to see more. I am hoping to get all of the AQA spec up by the GCSEs. I am losing my voice, as you may be able to hear. Sorry if I've left any of the coughing in. But yeah, I do hope this has been useful. Please do share it with who you think might find it helpful, and I will see you in the future. Bye!